Hello everybody, and welcome back. In this tutorial, we're going to be covering quiz number 31, which discusses equilibrium stability. Now, quiz number 31, it's the first quiz of the last topic of this course, which is the Rayleigh-Ritz method. Luckily for us, quiz number 31, easy peasy quiz. As you guys are going to see, this will set the speed running world record for fastest quiz tutorial on the internet. Now, why do we discuss equilibrium stability? Well, as you guys will see, when we start discussing the Rayleigh-Ritz method, it's all based upon having a stable equilibrium and potential energy. So it's not too bad, not too complicated. Again, nice easy quiz now. And then quizzes 32 and 33, we'll start discussing more in depth what is the Rayleigh-Ritz method and how do we utilize the potential energy, because we don't maximize the potential energy, we actually minimize it. All right, let's jump into the theory. So again, this whole quiz is about equilibrium stability. When is an equilibrium stable? When is it unstable? When do we have a neutral equilibrium? Or is there a case where we have no equilibrium at all? As we're going to see, there's going to be 4 cases, which is what I just mentioned. So equilibrium stability is actually determined based upon the potential energy of the system. And as you guys are going to see, the whole topic of this unit will focus around this idea of potential energy. So the first one is if the potential energy of the system is maximum. What does this mean? Well, this actually means that we have an unstable equilibrium. Now, on the other hand, if the potential energy of the system is a minimum, this means that we have a stable equilibrium. If the potential energy of the system is constant, it means that we have a neutral equilibrium. But we also have a fourth case that if the potential energy of the system is neither maximum nor minimum, then we actually have no equilibrium at all. And as we mentioned, the Rayleigh-Ritz method, which we're going to discuss in the next quiz, it focuses on the idea of having the potential energy being minimum so that we have a stable equilibrium. Of course, this makes sense if we're designing a structure or any sort of metal object. We want it to be stable. We don't want to have unstable equilibrium. It'd be very unsettling if we touch the building wrong and everything falls apart. It'd be quite scary. So this is the theory. As you guys can see, nice, easy, straightforward. Let's jump into the quiz. Alrighty guys, welcome to the quiz. As you guys are going to see, the quiz is just one nice simple question. And the question says, the figure below shows 2 different schematics of functions f representing the potential energy of a system and its derivatives. The point corresponding to the red dashed line in each figure represents the state of equilibrium. And what it wants us to do with these nice figures is it says, I guess question 1 or part A, the function in the first column represents, and it wants us to determine if it's a stable, unstable, neutral, or no equilibrium. And then, of course, question number 2 says the function in the second column represents a stable, unstable, neutral, or no equilibrium. So it's actually a very straightforward question. We're given the potential energy of the system and its derivatives, and we basically just got to determine what state of equilibrium do each one of these columns represent. So we're going to start with the first one here. And again, the first thing to keep in mind is this function f here at the top. This is actually the potential energy of the system. Now, we know that based on whether the potential energy is maximum, minimum, constant, or neither maximum nor minimum, we can determine the state of equilibrium. So if we look at this potential energy and we look at the system's equilibrium right now, that dashed line, we can see right here that this potential energy is actually at a minimum. And this is further reinforced because if we look at its derivative, we can see that at this state here, it changes slope. So this, again, reinforces that the potential energy in this case is actually at a minimum. Now, we said that when the potential energy of the system is minimum, this implies that the equilibrium is actually stable. So if we come down here, we can say, all right, the function in the first column, it has a minimum potential energy. Therefore, we know that this is actually going to be the stable equilibrium. And again, you guys may ask, Clayton, why is that again? Well, the potential energy of the system, it's actually minimum. So minimum. And this is something that we're going to use a lot moving forward in quiz number 20. No, we're actually on 30s now. 32 and 33. Because if we know the potential energy is minimum, then we know that the derivative of the potential energy with respect to whatever, it's going to be equal to 0. And what happens? This gives us a nice equation that we can use to solve for unknowns, as you guys are going to see. But that's quiz 32 and 33. We're not going to jump into that quite yet. Let's move up because the second question says, well, how about the second column? Well, if we look at the second column and its state of equilibrium, we can see that the potential energy appears to be maximum. So it's the opposite of column number 1. Now, in order to actually make sure that this is true, we look at the derivative of the potential energy, and we can see that, yeah, it has zero value, meaning that the potential energy is either maximum or minimum, and we can see very clearly that in this case it's actually maximum. So as we discussed in the theory, if we have maximum potential energy, this implies that we have an unstable equilibrium. So in this case, you're saying, Clayton, why is it unstable? Well, the potential energy in this case, so the PE, is maximum. So it's actually not too hard to determine if a system is in equilibrium. We just look at the potential energy and say, hey, is this maximum? Is this minimum? Is it constant? And if it was constant, we know it'd be neutral equilibrium. And if it was all over the place, neither maximum nor minimum nor constant, we know that we actually do not have equilibrium. So that would be answer D, no equilibrium. Luckily for us, the two functions given were very clearly defined as maximum or minimum. Therefore, we can define this question fairly simply. And that's it for the quiz, guys. Again, nice short quiz. Probably set a bunch of speed running world records. I don't mean to brag about that, but it's probably true. Someone should notify Guinness immediately. So thank you guys so much for listening. I really appreciate it. I will see you guys in quiz number 32.